All right, so today we're going to continue talking about material in chapter 2. So the title of chapter 2 is Matrix Algebra, and the first section talks about certain types of operations. So first of all, what is a matrix? We've seen them in chapter 1. And we start with matrix addition, subtraction, scalar multiples. And one of the extensions of scalar multiples is you can talk about what's called the inverse, the additive inverse of a matrix by taking all the entries and multiplying by -1. So we have the zero matrix. When we do multiplication, we're going to define something in a similar fashion, but as you know, multiplication is defined differently. You could, of course, have the same size matrices to multiply together. That's probably the easiest thing to see. However, as you know, not all matrices can be multiplied together. Some having different sizes can be multiplied and some cannot. So we'll take a look at those situations. So let's go to my Open Math site. Our notes from last time are right here. So just one page. The advantage of writing things on the tablet is I can save them, upload them back without having to do scanning and stuff. So my writing might not be the best, but at least it's easier for me to do it that way. So notes are there. I will put the posting of this class at the top when it is finished. So a reminder about the upcoming assignments. Weekly problem set is due at the end of today. Upload that to my Open Math. And then we'll keep the same pattern next couple of weeks. I did not come up with a third weekly problem set yet. I'll probably have that by the end of the weekend. So our lyrics homework is the practice. Weekly problem set are the problems from the textbook, and some of them are similar to the lyrics online. Some of them are a little bit different. I don't know who actually made up the homework from the textbook. A lot of times those are made by different people than the ones who actually wrote the textbook. So it kind of depends. So if you look at the first weekly problem set, there's a listing of the problems. And there are some choices here for sections 1, 1, and 1, 2. We talked about this in class on Tuesday. In particular, section 1, 2. If you were to do every single problem there, I think you could start now and maybe be finished by our next class. So there's a lot of them. So there are some choices here. And there's really no need to do all of them. So if you can do 1 or 2 from each section and feel pretty good about how you solve those, I think that is certainly good enough. So upload them as Word or PDF, and then I will grade them. What will happen is if you uploaded them in my Open Math, I will grade it that way and send it back to you. If you actually turn it in class, which of course can't do today, but if that's the option for next time, I'll just actually grade it and just give it back to you in class. So if you go to, oops, that's not what I wanted. Course content, we're essentially done with the first unit. So sections 1, 1 through 1, 6. So we are in the second unit, which is called Matrix Algebra. So the first 3 sections are kind of all combined. These are the learning objectives. I got the textbook right there. Those might be old lecture notes. I will update those or maybe change those as you see them, so they kind of relate to our class. And then some videos for the different types of matrix operations and applications that we're doing in this particular section. So addition, multiplication we're talking about now. Inverses come later. Scalar multiplication is also something we're doing right now. So that's where you can find all that. So let's go ahead and continue on in the chapter 2 material, talking about matrix multiplication. Now our book talks about it first as a matrix multiplied by a column vector, so we can relate it to the systems of equations that we solved in the first chapter. But remember, in general, your matrices can be of any size. So let's review that real fast here. Right. So as a reminder, when you're doing matrix multiplication, order does make a difference because we need to look at rows of one matrix and the columns of the other matrix. So if matrix A is an M by N matrix, matrix B can have as many columns as you want, but it must have the same number of rows as the number of columns in A. So these two numbers must match up. So if you look at it this way, if A is an M row and N column matrix, and B is an N row and a K column matrix, their product can be calculated and we can predict what the size of that is going to be. This could be the number of rows of matrix A and the number of columns of matrix B. So if you start with, for example, let's do a 3 by 3 here. Think about the possible matrices you could write down for matrix B that would be able to be multiplied by this matrix right here. And the only thing you need to make sure of is the number of rows in matrix B has to match the number of columns in matrix A. So you need to have something with 3 rows. So let's do a 3 by 2, for example. So 3 rows and 2 columns. Let's say this is matrix B right here. So we can make a prediction about the product. Okay, I told you this was going to happen, right? Okay, let's see. I'll just switch my slots here. I didn't like that either. Okay, didn't like that either. Right, so going back to this example right here. We have in matrix A is a 3 by 3, matrix B is a 3 by 2. So we know when these two numbers match up, we can do a product. And not only can we write down what the product is going to be, you can also say the product is going to be a 3 by 2 matrix. So what's nice about setting it up like this is you can make a prediction as to what you're going to put in the first slot. So first row, first column. It's going to be the first row and first column of both matrices. So if you do essentially the product, 3 times 2, 0 times 5, and then 1 times 6. You will then add all those entries together. So if you've seen, we usually do this in 3rd semester calculus, a dot product. That's exactly what you're doing here. It looks exactly like a dot product. So if we think about the dot product of two vectors, that's what you're doing here. You multiply corresponding terms and add them up. So you can also make the prediction. This is the first row, first column entry. If you want the second row, first column entry, then you're going to do this product, 4 times 2, -1 times 5, and then 7 times 6. If you want the third row, first column, do the exact same thing, 2 times 2, 5 times 5, 8 times 6. So we've kind of talked about this in class. How do you know students are multiplying matrices together? And you see them doing this all the time. Matching up the rows, matching up the columns. So by actually illustrating it this way, you can see how it's done and also relate these entries to where they came from in the original two matrices. So the red circled rows and columns, first row, first column. So think about A sub 1, 1. Second row, first column goes here. Third row, first column goes here. So that's the new first column of the product matrix. And then if you do the second column, you'll do the exact same calculations. Your first numbers will be the same. And then your second numbers will come from the second row. So for the second column, first row, it'd be 3 times 1, 0 times 8, and 1 times 7. 4 times 1, -1 times 8, and then 7 times 7. Then last row is going to be 2 times 1, 5 times 8, 8 times 7. So we've got lots of nice colors here. But you can, of course, use technology to get your answers here. But illustrating it this way, you can see how the product is formed, and you can see what's kind of the same, what's different about the two columns. Those numbers all come from the first matrix. These numbers all come from the second matrix. So the 2 and the 5 and the 6 all come from column 1. The 1 and the 8 and 7 all come from column 2. So everything stays the same in the first slots, coming from the first, second, third rows of matrix A, and then it changes in the second slot depending on what column you're using. So to finish up this problem, get an answer here. See if I can do this all in my head. 6 plus 0 plus 6. 8 minus 5 would be 3, and 3 plus 42 would be 45. 4 plus 25 is 29. 29 plus 48 is going to be 77. And then your second column will be 3 plus 7. 4 minus 8 is -4. -4 plus 49. Also 45. And then 2 plus 40 is 42. 42 plus 56 is going to be 98. And there's your 2 by 2 matrix. So we talked about things being linear combinations. By writing it out this way, you can see those linear combinations when you multiply. Where does the first number come from? Where does the second number come from? And that's how you get these entries in the product matrix. So this is AB, and AB is a 3 by 2 matrix. So the other thing is, when you do multiplication, we talked about this with addition. When you switch the order, is it going to be possible? Well, first of all, you'd ask, are you going to get the same answer? That shouldn't be your first question here. Your first question here should be, can we even calculate B times A? Well, B is a 3 by 2 matrix, and A is a 3 by 3 matrix. We got a problem. Those two numbers do not match up. So BA doesn't even exist. So we'll talk about when the product exists can be true that they are going to be equal. So we have seen that our systems of equations can be thought of as a system. A is going to be a certain size matrix. X and B are both going to be column matrices. So depending on how many rows you have, it's only going to have one column. So if A happens to be 4 by 3, for example, then B would have to be a 3 by 1. And then when you do the product, you write that as a vector, sorry. So when you do this as a product, you can predict the size of this matrix here, and it's going to be a 4 by 1. So column vector, column matrix, 4 rows, 1 column. So you think about what a matrix A is going to look like here. 4 rows and 3 columns. Each variable you're going to get is going to correspond to one of these rows. So your final answer is going to be a 4 by 1 matrix. So when you have 4 rows and 3 columns, it's the columns that you're going to use for this calculation right here. So if X is a 3 by 1, like say, for example, the variables are X and Y and Z, you're going to need to come up with an answer for each of the 4 equations. So this is why this can be a 4 by 1 matrix. So that's kind of how we use matrix multiplication. At the end of, I think, section 2.3, there's another application, which we may or may not have time to do today, but we'll go ahead and look at it when we get to the end of that section. So going back to this linear combination idea, if I took the first column of this matrix, and this is the product matrix, we could think of it as a linear combination. That's how we calculated it. So you get each of these entries that you see right here. So how did I come up with 12? 3 times 2 plus 0 times 5 plus 1 times 6. How did I come up with 45? 4 times 2. Negative 1 times 5. And 7 times 6. And then 77 is 2 times 2, 5 times 5, and 8 times 6. So when you think of this as a linear combination, you can once again see that the 2 and the 5 and the 6 are all going to be the same. So if I take 3 times 2, 0 times 5, and 1 times 6, that's going to produce the 12. So if we think of the columns of B, we can think of the answer as being a linear combination. And that's, like I said, one reason for thinking of it this way. You can actually see how the linear combination is being formed. So you say, how do you get the 12? Well, the 12 comes from the 3, 0, 1, which is the first row, multiplied by the entries in the first column. So now we're going to go back and look at a system and talk about when the system is going to have solutions and not have solutions, and look at REF or REF. So go ahead and take a screenshot here, Gina, if you want to. And let's take a look at this question again. For a system of linear equations to be consistent, we know consistent means a solution exists. It could be unique, could be an infinite number of solutions. vector B, so the column vector you see here, needs to be a linear combination of the columns of A. So back on the previous example, you saw how the product was formed. We're now going to do this for a system of equations. So let's start with a system here. 2x plus y plus 3z plus 3w is equal to 1. Y minus z plus w is equal to 2. Then negative x plus y minus 3z is equal to 3. So we have 4 variables and we have 3 equations. So you think about the matrix that you're going to form here. Coefficients are going to be 2, 1, 3, 3, 0, 1, negative 1, 1, negative 1, 1, negative 3, 0. That'd be the coefficient matrix. And then if we want to actually write this as a system, your column matrix for the variables, x, y, z, and w. And then your column matrix for the solution. So 1, 2, 3. So there's your 3 by 4. Here's your 4 by 1. Here's your 3 by 1. So that's how we write it as a matrix system. So this is matrix A. There's column vector X and column vector B. So now when you're doing this, you set up the augmented matrix and then go for your either REF or RREF. So let's do it that way. Set up the augmented matrix. And save us a little bit of time, I have the REF for this one. Actually, it's RREF. And let's go from there and write down these solutions. So because you have more variables than equations, we're not certainly going to get a unique solution, but will we get solutions at all? So we need to look at RREF to figure that out. Okay, there's the first row. Here's the second row. And then here's the third row. So we talked about rank before. The rank of this matrix right here, so this matrix A by itself, is going to be 2. So if this is matrix A, the rank of A is going to be 2. Notice, however, if you look at the entire matrix, so the augmented matrix with A and the solution vector right here, that rank, this is the way our book writes it down. It kind of writes it as the augmented matrix A with the column vector. It's not really B though, right? Variable there. Let's call it vector C. So that's vector C. Notice that rank is equal to 3. If you were just looking at this compared to the original system, and I were to ask you, will this system have a solution? The answer is no. Last row tells us that 0 is equal to 1, which is a false statement. So from RREF, the original system has no solution. So this is another way of noticing when a system will be consistent or inconsistent. If the rank of this matrix is the same as the rank of the augmented matrix, you'll have solutions. But if this number is bigger, And the only way it's going to be bigger is one bigger. Notice you have leading one here, leading one here, leading one here. So that makes the rank of this matrix 3. So from our REF, the original system has no solutions. So what that means is B, so vector B here, is not going to be a linear combination of columns. Okay. I said columns and I meant, I want to write combination here. Of the rows of A. Because if it was, we can write 1 as a certain number of X's, a certain number of Y's, a certain number of Z's, and a certain number of W's. And this is telling us that it's not going to be possible. So identifying whether something's going to be a linear combination or not, we can then see whether our system is going to be consistent or inconsistent. So this one is going to be an inconsistent system, meaning no solution. So if we did have a consistent system, we'd be able to write vector B as linear combinations of the rows of A. I'll give you a chance to do another screenshot here. So now we're going to talk about this system compared to its homogeneous system and how those two compare in terms of finding solutions of the general system AX is equal to D. Right, so a couple of things before we do this. If I take the 0 matrix and multiply it by our column vector, vector X, you would not expect to get anything other than a vector or column vector of zeros. So it does not matter what X would be here, you're multiplying all the entries by 0. So a 0 matrix is just a matrix any size that has all entries being zeros. So you can make an M by N matrix of all your entries being 0. So whatever size you would need in order to make the product defined. So an M by N matrix consisting of zeros. So 0 times the column vector X is going to produce the 0 vector that we see here. And similar answer is if you take a matrix A and multiply by the 0 column vector, what's going to happen in that case right there? Since you're going to multiply all the entries in matrix A by 0, that should also produce the same result. So this is true for all matrices, also true for all column vectors. The other matrix we're going to be spending a lot of time with is the identity matrix. And the identity matrix is usually denoted with capital I. And for the most part, we're going to do these with square matrices. So here's the example of the 2 by 2 identity matrix. When we talk about identities, the additive identity is the number you would add to a number to not change a number. So 3 plus 0 would be 3. 1/2 plus 0 would be 1/2. So 0 is what we call the additive identity. The multiplicative identity is the number you would multiply by to keep the number the same. So one number times 5 would give you 5, for example. A number times 1/2 would give you 1/2, and that number is 1. So this is acting like a 1, but remember when you're multiplying, you need to make sure that you're answer matrix is the same as the matrix you started with. So if you have a square matrix, and you say, I do not want to change this if I multiply by a second matrix, that's going to produce the same answer right here. So I want to keep the 4 in place. So a natural response here might be, well, 1 is the multiplicative identity, so why not put all the 1s in those slots right there? Then you check it, it doesn't work. 4 times 1 gives you 4, good. However, to get the other part of this entry, you also have to do 5 times 1. And that does not give you 4, it gives you 9. So that's too many 1s. So you realize, what's my problem here? I want the 4 times 1. I do not want the 5 times 1. So I make this entry a 0. And now I got my 4. Does that work for the 2? 2 times 1 is 2. 7 times 0 is 0. Looking good. So your first column is in good shape. However, you're going to find the second column suffers from the same problem as the first one did. 4 times 1 is 4. 5 times 1 is 5. We want 5 here, not 9. So you realize that we do not want the 4 there. So the first step is to do 4 times 1, make it a 0. And then you only have 5 times 1. And it gives you 5. Does that also work for the 7? 2 times 0 is 0. 7 plus 1 is 7. So that one actually works. So it's easy to show why you need 1s in these 2 slots. For a 3 by 3 matrix, it's 1s along the diagonal and 0s everywhere else. So you can kind of generalize and talk about the n by n identity matrix has 1s along the diagonals, however many rows, columns you have. And then you essentially have 0s everywhere else. So this is some notations that some books use to denote the n by n identity matrix. What's nice about the identity matrix is you can certainly do a matrix times the identity matrix to produce the original matrix back. It also works the other way. You can do I times A and you get the original matrix back. So this is a case where commutative property actually does work. If the matrices are both squares, you can at least multiply those two together. And in addition to multiplying them together, you end up with the same matrix that you started with. All right, so let's take a look at this result right here. Let's go back and consider our system AX is equal to B. If you look at this system, this is the associated homogeneous system. So everything is the same for matrix A, same variables, except now instead of your last column just being some numbers, they're all going to be 0. So it's the associated homogeneous system to the original. And let's say we have a solution, we'll call it x sub 1, to this system right here. Now, if the system only has one solution, that's of course the one you want to use. But for ones that are consistent with many solutions, you just take one of them. So let's say given x sub 1 is a solution to that system right there. And the associated homogeneous system, you could write down a solution for that. So we'll call it x sub 0. So 0 homogeneous. You know that the homogeneous systems have trivial solutions, all the variables being 0. We're talking about a non-trivial solution here. So this is a non-trivial solution to the associated homogeneous system. Then, if you want to find another solution to the original system, it turns out all you have to do is add those two together. And we'll do an example here to illustrate this, but this is what the result is saying. I think it's, I'm not sure it's a theorem in the book. It might just be a, so adding these two together, this is also going to be a solution to the original system. So this is something that's going to help us come up with a general solution to one of these systems that you see here. Solving the associated homogeneous system, getting a non-trivial solution from that, and then adding it to a solution here, and then talking about how we could generalize it. So we're going to need some more room here. So I'm going to take a picture here, Gina. Okay, so you remember the result. If you take a regular system, ax is equal to b, take the associated homogeneous system, ax is equal to 0. Take a particular solution from both systems. If you add them together, you'll get another solution to the original system. So let's start with this system right here. So if I will use x sub 1 as the first variable. And we got 3 variables for this one. So here's the original system. So 2 equations and 3 variables. Let's write the augmented matrix here. Okay, and save us a little bit of time. I'll give you the our REF here. Okay, so for this one, you can see the rank of matrix A, which is right here, is 2. The rank of the augmented matrix, also 2. What that means is the system will be consistent. So we're looking for solutions here. The number of ones you see here related to the number of columns. One more column, then you have ones, which means we're going to need 1 parameter. So when you write down your general solution here, looks like this is going to be our free variable. We'll call that one t. X sub 2 we'll write down in terms of x sub 3. So it's 5 minus 27 times t. Then x sub 1 is going to be 2 minus 12 times t. All right, so that's our general solution. This is our parameter. So this is your free variable, and then these are going to be basic variables. So I don't know if you've worked with any matrix algebra, maybe some more like theorem results. If you've done these applications, I know we do these in our like finite math class. Anything that looks like this is going to be considered a basic variable. Anything where the ones are not there, meaning we're going to let x sub 3 be t, is a free variable. Free in this case means parameter. You select t before you can calculate values for x sub 2 and x sub 1. So a couple different ways you can write this. We write it as a column vector. And you could first write it this way. X sub 1 is 2 minus 12t. X sub 2 is 5 minus 27t. And X sub 3 is t. So here's another way to write the answer. There is your particular solution. So this is going to solve the system. This is kind of the variable part. So determined by this vector, any multiple of that vector right there. So this is a solution to the original system. So if we call that X sub 1, this right here is a solution to the associated homogeneous system. Now to show that, if you start with the original system again, but use zeros instead of the 0 and the 1. Your matrix will look pretty much the same, except this entry here will be a 0 instead of a 1. And it turns out that if you go from this matrix to RREF, it's going to look almost exactly the same. The only difference will be you're not going to have a 2 and a 5 here. You're going to have a 0 and a 0. So you can verify that on your own if you want to. So RREF looks like this. So the coefficient part, when you do RREF, looks exactly the same. So these two calculations, the only difference is you're going to get some numbers here for the non-homogeneous system. So by looking at this, you say, what is the general solution going to look like? There's your parameter. There's X sub 2. And then here's X sub 3. And where does the 1 and the negative 27 and the negative 12? Sorry, that should be X sub 1, not X sub 3. You say, I've seen those before. Yeah, they're right here. So this is a solution to the homogeneous system. This is a solution to the original system. So if you want a new solution to the original system, it's essentially a multiple of this vector right here. So if t is 1, here is a particular solution to the system. Call it X sub 3. That's when t is equal to 1. When t is equal to 0, you get this vector right here. When t is equal to 1, you get this vector. By adding it to this vector right here, it's going to give you a solution. So 5 times negative 10 minus 2 times negative 22 plus 6 times 1 is supposed to be 0. Negative 50 plus 44 plus 6 is indeed 0. So negative 2 times negative 10 plus negative 22 plus 3 times 1 is supposed to be 1. 20 minus 22, negative 2 plus 3 is 1. So by adding these two together, gets you another solution. So we're going to use this again in a subsequent chapter. We do the linear transformations in some more detail. We're going to talk about transformations right now, but this is kind of an introductory lesson to transformations. After we talk about some more matrix algebra, we'll do some more with the transformations. So go ahead and do your screenshot here. And let me know if you have any questions on any of that. All right, so let's do a little introduction on this idea of transformations. So as an initial example, we take a vector in the plane. Our usual notation for vectors in the plane is the tail is down here at the origin and the tip is somewhere else. So let's take this point right here in the first quadrant. And let's use a specific example and we can generalize it. Let's say this point is 5, 2, for example. There are some ways in which you can transform this vector. You can think of it as vector 5, 2. Maybe we'll write it as a column vector. So one transformation you can do is you can flip it over the x-axis. So think about what that would look like. You could also flip it over the y-axis. Think about what that would look like. Or you can take it and flip it over the x-axis and then the y-axis. Think about what the result would look like there. Not sure my picture is to scale, but it should be pretty close. With this example, we can make predictions as to what these coordinates are going to be. So this one here, if we take the graph and flip it over the x-axis, we think about what's going to change, what's going to stay the same. Your x coordinate should stay the same. Your y coordinate, however, goes from 2 down to -2. So we talk about this as a transformation of the original vector. If you flip it over the y-axis, think about once again what changes, what stays the same. So now when you do the y-axis, it's the x's that switch, and then the y value stays the same. So the 5 turns into -5. Y stays the same. If you do one after the other, and actually order here doesn't matter. You can do it over the y-axis and then the x-axis or the other way around. You end up down here, which means you changed both x and y. Right, so those are 3 different transformations you can do on this vector. The way we're going to define this later, and we're mostly going to do what are called linear transformations. Think about, is there a matrix that we can multiply by this vector that will produce each of these 3 results? So vector V, that's the original one here. We're going to multiply it by vector A and try to represent the answer also as a column vector. So what matrix could we use to produce that vector? What matrix could we use to produce this vector? What matrix could we use to produce this vector? Now the answer is going to be a 2 by 1. This is 2 by 1. So the original matrix has to have 2 columns. So we could play a little guessing and checking here, but we want to start with, let's do the first one. We want to start with vector V. We want to end up with, let's say, the vector in the second quadrant. So changing the y coordinate, keeping the x coordinate the same. And let's, for simplicity, assume that we're going to get a 2 by 2 matrix to start, because 2 by 2 should be able to be multiplied by 2 by 1. So what would those 4 entries have to be if I want to multiply vector V, column vector, by matrix A to produce this new column vector? That's a way of representing transformations. You can see the picture. I say I picked this up and move it here. Well, we're going to try to set up as a matrix. So you could think of this as a system. Let's actually do the first one as the system. And then the other ones where you do a little guessing and checking. So the system that you're solving here for a sub 1, a sub 2, a sub 3, a sub 4 is going to be 5 times a sub 1 plus 5 times a sub 2 is equal to 5. 5 times a sub 3 plus 2 times a sub 4 is equal to -2. So there's your system. So you got to come up with variables that are going to work here and here, producing 5, variables working here and here to produce -2. Now, really, this is a 4-variable system, and there are only 2 equations. So you can try to think of it using a matrix. It might be better to do the guessing and the checking here, because this equation only involves A1 and A2. This equation only involves A3 and A4. So if you're guessing a bunch of zeros and ones and -1s are going to be working here, I think that's a pretty good guess. If you look at this one, for example, A1 could be 0 and A2 could be 1. That would produce a true statement here. Here, however, I think we're stuck. A3 has got to be 0. The only way to get a -2 here is to make A4 equal to -1. So let's try this. A4 is -1. A3 is a 0. One of these is going to have to be 1 and the other one's got to be 0. So if we want to be consistent here, let's see if this is going to work. Let's put the 0 here and the 1 here. And let's see if that's actually going to work. So 1 times 5, 0 times 2 produces 5. 0 times 5, -1 times 2 produces -2. So I think you can see if I put the 0 here and the 1 here, you would not get the result that is desired. So this matrix A is called the transformation matrix. So if I want to know how to reflect a vector over the x-axis, I could take the vector representation you see here and multiply it by matrix A. So matrix A, which is done by this matrix right here, is called a reflection matrix over the x-axis. Knowing that, you can come up with similar matrices for the other 2 transformations. So how would I get a -5, -2? How would I get a -5 and a 2? And I think you can see these are going to be variations of some type of identity matrix. So if I want to describe matrix B as a reflection over the y-axis, remember this one changed the y-coordinate, and notice where the -1 was. Reflection over the y-axis should change the x-coordinate. So if you're thinking I should put the -1 up here instead of down here, you are thinking correctly. So this should be a y-axis reflection. So it should change the x-coordinate, keep the y-coordinate the same. If you want a matrix that's going to do both, so x and y-axis reflection, both coordinates need to change from positive to negative or from negative to positive, depending on the original point. There it is. So what you're looking for here is a matrix that can be multiplied by the vector that will produce this new position of the vector, which we write as a column vector. So flip over the y-axis, flip over the x-axis, flip over the x-axis, and then flip over the y-axis. So later when we do these problems, big T is going to represent the transformation. We're going to go from a particular space to another. And what all that means is you're going from this case, a vector in 2 space, R2. And then you're going to end up with another vector in R2. So this is a vector in R2. This is a vector in R2. So the matrix we're going to use to describe that is going to be a 2 by 2 matrix. So this is a transformation from 2 space to 2 space. In general, you can do it from any space to any other space. We're going to initially do the ones we can actually see. Here's the notation we're going to use. The transformation will be described by capital T. You're going to transform vector X, and then your transformation will be performed by operating. So the vector X is going to be multiplied by A. So A is called the transformation matrix. So this allows us to do a general statement about going from M to N or vice versa. So Rn or Rm. And then the matrix will be sized accordingly. So this is going to come from either the first set, and then this is going to be, after you do the product, will be something from the second set. So we're doing it for vectors just to kind of illustrate how it's going to work, but these numbers can be anything. You can have any dimension that you want. So when the book writes this down in general, they usually write down this way. Your transformations are going to go from R sub n, or not R sub n, R and n space to M space. And then when you write down the statement here, you can make the prediction of what size matrix A is going to be. So in this particular case, A is going to be an M by N matrix. That'll perform the transformation. And notice the order here. M is the space you end up in, N is the space that you start with. So it didn't really matter here, both spaces were R2, but our 2 by 2 matrix, here in general, it's going to be an M by N matrix. So if you've taken, I don't remember, Gina, if you took Calc 3 or not, give me a thumbs up if you have. Okay, so you may have seen, we're talking about lines and planes and projections. If you were to take a vector in 3 space, for example, one transformation you can do on that vector is you can project it onto the XY plane. You can project it onto the other planes, YZ, XZ. You could also project it onto one of the coordinate axes. What kind of matrix would you need there to project, for example, this onto, and this is supposed to be 3 dimensions, right? The XY plane, for example. So you need to come up with a 3 by 3 matrix that's going to take any general point, which is representing a vector in 3 space, and essentially make the last coordinate 0. So it's similar to what you see here, but now in order to make the 0, you need to multiply your vector by this matrix that you would define. That's going to produce a 0 component for the last one. So projecting that onto the XY plane. If you want to project it onto the y-axis, for example, then you would use a different color here. Make all the other coordinates 0. So 0 for the x, b for the y, and then 0 for the third coordinate. So this would be a projection onto the y-axis. This is a projection onto the xy plane. So you may have seen that before in Calc 3. We can now talk about them using this idea of a matrix to represent that particular transformation. A couple of other ones they talk about in the first section. You saw the reflections. Those are all there. You can do a rotation. You can think of this as rotating. Think about what that matrix would be. It has something to do with trigonometry, as you might guess. I'm just going to take a picture here. I'm going to just erase a little bit and show you one more transformation. But I don't want to get rid of the entire screen yet. Okay, so another type of thing you can do, and you can use the same picture, is a compression or a stretch. It's interesting, we're talking about this in our class. I just did this in college algebra yesterday. They're talking about just transforming essentially functions and moving them left or right, moving them up and down. There are ways in which it can be done. You can look at a picture. You can think about equations. You can put in words like, I want to move this 5 units to the right. One of the transformations that I think it's easy to see but kind of hard to write down are the compressions and the stretches. So if you're doing that for this vector right here, I say I want to make this vector smaller, less length than the original vector. I'm going to be changing both of these components. And the question is, how are they going to be changed? What happens is you end up multiplying by a constant. Now, if you make something smaller, you make something bigger, it depends on, or that will be determined by what constants you use. So for example, if I wanted to take each of these components and have them, so go from 5 to 5 over 2 and then 2 over 2. What kind of matrix would produce that new vector? That would be called a compression. We're dividing each of the components by 2. So since you're doing it for both of them, think about what that matrix would look like. Would it have to be a matrix that looks like this? So if I took my original vector right here, 5, 2, and multiplied it by matrix A, which has 1/2 in these 2 slots, is that going to give me this new vector here? It should. 5 times 1/2, 0 times 2. 0 times 5, 2 times 1/2. So depending on what this number is, it could be a compression, it could be a stretch. So the stretchy vector would look like this. Oh, that's hard to see. And then you can think about it as multiplying by a number. So if we said do multiply everything by 2, then your new components would be conform. And then think about that translation matrix would look like. So those are also talked about in this section. I find it interesting, they talk about 2 other ones, which I think are pretty obvious. The identity transformation, what would that do to vector 5, 2? Not a thing. So matrix A would essentially be the identity matrix. You don't want to change anything, multiply by the identity. The other one is making the original vector the 0 vector. It's like, I suppose you could do that, but why? That would be multiplying everything across by 0. So I like starting out with these types of examples because you can see it. You can actually write down what the matrix looks like, because we are going to be doing this in general. And identifying these as linear transformations. So this is kind of the general statement you see here at the bottom. Because when we're going in 2 space and in 3 space, it is possible to see those things. When we extend these to 4 space, n space, m space, we aren't always going to be able to see them. But we can still set it up as a matrix We'll know what the size of the matrix is. We'll maybe describe what our transformation is supposed to look like. So Kevin, that's a little introduction there. All right, you can do one more picture here if you want. And next class, we'll talk a little bit more about the matrix multiplication and the properties you can get for matrix multiplication. I'm going to kind of list a few of these right now and maybe look at some more of them on Tuesday. But if you think about matrix multiplication, we had written down a couple of these before. If you take a matrix and multiply by the identity matrix, the matrix stays the same. So IA, AI turns out to be A. This might be a surprising result. If I want to do a product of three matrices, A, B, and C, you can do the product of the first two and then multiply by the third. You could do the second and third and then multiply by the first. Now, order here does make a difference, but either one of these can be done to produce the product ABC. You can't do CBA. That one doesn't necessarily give you the same matrix, but the first order actually does not make a difference. You do A times B first, or you do B times C first. This is called the associative property. Now, of course, all these are only going to work if your matrix multiplication can actually be calculated. So if these are all square matrices, for example, no problem. But if this is like a 3 by 2 and this is a 2 by 4, then C is going to have 4 rows in order for that product to be defined. So remember, multiplication of matrices is not commutative. I don't know why I put that in parentheses. I was going to put the whole thing in parentheses. So in general, you can't switch the order and even get a product, let alone have them be the same. But associative is true. So matrix operations are a good example of something that is associative, but not commutative. Because there are some students who just think, oh, it works for commutative. I take 2, I should be able to do it for 3 and 4 and 5, 6, et cetera, et cetera. So this is a good example of something that works for the associative case, but not the commutative case. I'll write down a couple of these other ones and then we'll end it for today. You have some type of distributive property that's going to work. When you do a scalar multiple, order here does not matter. You do the scalar multiple times A. You can use scalar multiple times B. And then multiply those two together. This is something we need to investigate. What happens if you take A times B and then take the transpose? Is that going to be the same as the transpose of A multiplied by the transpose of B? Or is it giving something else? So I'm going to leave this as a question mark. So to be determined. TBD, to be determined. Again, one last screenshot there. We'll pick things up on Tuesday right there. And so some reminders about just the assignment due at the end of today. And then you can start working on the next lyrics homework, which is due on Tuesday. I think it's a little bit longer, but get that done before you work on the next weekly assignment.